Well, thank you very much. I would like to thank the organizer for the opportunity to give these lectures. So I will divide my lectures in two parts. The first two lectures will be mostly devoted to the geometry of the space of arcs on a variety. So throughout these lectures, I will denote by X a complex algebraic variety. And so what is the arc space of X? So denoted by X infinity. This way. And to the first approximation, I can think about this as space of arcs which are germs of curves on the variety. But I rather think about as maps from delta alpha to X, where delta is inside C is some very small disk. So you think about delta being a very small disk, until like this inside complex numbers, but in fact, I would typically picture the disk in the following way, thinking about usual that the complex plane, in fact, is a line over the complex numbers. And I just look at the space that all these maps. But in fact, I rather think about X infinity, not just as a set of these arcs, but really as a scheme. So in order to describe a scheme, one way of describing a scheme is to tell you what the points are. And I can think about the closed points would be the points parameterized over C. But in fact, as a scheme, it's best to give points to describe, for instance, what is a k-value point. A k-value point on the space of arcs is simply a k-valued arc. On X. So it will be a map A, and maybe I want to make better definition of what I mean by very small disk. What I think about is that I look at the power series ring in one variable with coefficients in K, and I look at the spectrum of this ring. And then I look at a map from the spectrum into X. So I'm thinking about the disk, this infinitesimal disk at this point, defined over capital K. We have a closed point here, and we have some generic point. And the map alpha, it just takes this little germ somewhere on the variety. You're going to have the image of a closed point, and then somewhere the image of the generic point. So 0 will be the closed point. And eta will denote the generic point. So notice that I didn't really explain why this really exists as a scheme, but let's grant this for a moment. Every time I give you an arc, in particular, I pick up a point on X. Suppose that for a moment this is actually really defined over the complex numbers too. So capital K is actually complex numbers. Then if I look at 0, this is a closed point, it will map to some closed point on X. And so this gives also a natural map, which is called a natural projection. Goes by pi x, or sometimes you have to kind of write pi. It goes from X infinity to X. It just takes an arc alpha to its value at 0. And it's a canonical projection down to X. So one thing you notice that for actually the topic of these lectures, I want to relate arcs to valuations on the variety. So one thing you notice is that every arc alpha from spec k t into x defines a valuation. The valuation, I'm going to denote by valuation to alpha. So this is defined on the local ring. I look at the local ring of x at the base of the arc, variety as alpha 0. So this is just one point in x. And notice that now if I take k to be an extension of C, then this point I don't know actually to be closed. So some point on the variety. And maybe I remove the 0. So the way we define valuation is that first I pull back by the arc, and this brings me to kt. And then from this, I just look at the order of vanishing, given a power series in T, look at the order of vanishing at 0, so the order of the power series, and this goes down to n. So you always have a valuation like this in the local ring. And so now the question is, when do you think I can actually extend the valuation from this local ring to the whole variety x, or to the function field of the variety x? And so this extends to a valuation on x. So there will be valuation alpha from the function field of x going through the function field of the arc, and then go to z. This if and only if the image of the generic point is equal to the generic point of x. And in fact, most times we will focus on arcs. We satisfy this property and look at the valuations that these arcs define on the variety. So let me give an example of the arc space of a variety. Probably the best example to start with, some examples. So the best example to start is suppose I take as x an affine variety, an. And so to give a map alpha from spec k bracket t into an, that's the same as giving an nupel of power series. Start from one for each coordinates in an. And so you just think about this, if you like. This is just a Taylor expansion. If you think about arc as being defined from a germ of a curve, there will be just a Taylor expansion of a parameterization of the curve. And so what does it mean? It means that when I think about the arc space of an, so I look at an infinity. So in order to give an arc, I just need to give you the coefficients on these Taylor expansions. So for each coordinate in an, I have infinitely many free parameters to give. And there are no relations among these parameters. So what I see is that the arc space of an affine space is isomorphic, so infinite dimensional affine space. And and a point given here, just given by this coordinate aij, for all possible I and j with other components. So you think about this as being the components or the coordinates of an arc inside this infinite dimensional affine space. So So for a second example, suppose now the x is defined by some polynomial equal to 0. So you have a polynomial equation of x as, I say, an hypersurface inside an. Or more generally, x maybe is an affine variety. Instead of one polynomial, I have several polynomials defining the ideal of x. And I can ask about what is the arc space of x. So what you do is you start with an arc. You start an arc on the affine space. And now you ask whether this arc belongs to x. In order to belong to x entirely, you need to have that the power series expansion of the arc in the coordinate that satisfy the polynomial identically. So it means that when I plug in this power series, I need to get 0 as in power series ring. And so what is this? This itself is a power series in T by plugging in. And what I need to have here, I need to have all the coefficients equal to 0. So the coefficients are going to be polynomials in the components of the arc. So what you see is that I realize x infinity inside an infinity as a subscheme which is defined by infinitely many equations in infinitely many variables.
That is alpha in x infinity.
Yes, thank you. And this, in fact, is how you construct the scheme. You construct it locally for an affine variety, and more generally for an affine scheme. You define the arc space in this way. And then the general case, you just follow the construction from the affine case by gluing. So, well, you need to check that these definitions are compatible with other intersections and so on, but that's how you construct the arc space in general. To be honest, this is not the only way you can actually define the arc space. Alternatively, you can define the arc space as a limit of J schemes. So the arc space of x will define the limit, the inverse limit of the J schemes of x, where you think about the J schemes of x given by dm, say dm is a spec kt modulo t to the n plus 1 to x. So the difference between the definition of the arc space is that in arc space I look at the full power series, and here I truncate power series of polynomials, doesn't matter, up to degree m. And I send everything to 0 after that. So the fact is that this inverse limit is gotten by a towers of projections. So you have a projection from xm to xm minus 1, which is given by the inclusion. So this is the n minus 1. This is you can think of this being an n minus 1 neighborhood of the origin in the formal disk, and then of course will sit inside the m's neighborhood. So if I give a jet, an m jet to x gamma, then I can always restrict it to one smaller neighborhood and get an m minus 1 jet. So this gives a towers of projections. And you take the inverse limit on these tower projections. And this is, in fact, a scheme because these are affine maps. But one thing they should remark from other construction is that, even when I start from an algebraic variety, which is a very nice object, in general, unless the variety is zero-dimensional, x infinity is not Noetherian. And it's not of finite type. So it's a kind of a complicated object from the point of view of algebraic geometry. So the question is now, what can we say about, for instance, the topology? So maybe I should mention that as a scheme, the arc space comes with the Zariski topology, which agrees with the inverse limit topology of the J schemes. And so what can we say? Even forgetting about the scheme structure, that's actually a very hard question in general, but what can we say about the topology of the arc space? So the first remark they can make is that if X is smooth, then each projection from xm to xm minus 1 is an affine bundle. So it's an n bundle. A n bundle, where n here for me now denotes the dimension of x. And the way you prove this, in fact, there are two ways of proving this. One way to prove this is first to actually think about the case of an affine variety. And now you check that the truncation map, means just truncating these Taylor expansions from degree n, degree n minus 1. And when you truncate from degree n to n minus 1, you just have n free parameters. So this gives you the fiber. And then if you have a smooth variety in general, then you take an auto-normalization and you check that this is compatible with the arc space and the projection maps. So you deduce the property on any smooth variety. So, but stress that this is true when a smooth variety. So, but because of this affine bundle, in particular, these are very nice map, are smooth, surjective. And so, for instance, some consequences of this is that the first consequence I want to draw is that the space x infinity is irreducible. And in fact, for every irreducible set, S inside X, so when I talk about a reducible set, I'm thinking about a constructible set, but I think about a closed set as well. That's fine too. The inverse image under the projection map to S inside X infinity is also irreducible. So, in general, these kind of properties, they actually fail if X is singular. If X is singular, the last property may fail. So it's no longer true that if when I take an inverse image of an irreducible set in X, if this irreducible set goes to the singularities, then I still preserve irreducibility on the arc space. So the problem here is that the maps, the truncation map, from xm to xm minus 1 are complicated. And I'm going to put, it's exclamation mark. This is really a very delicate issue. So it's not just a little bit complicated, they're really complicated. And understanding the inverse limit over towers of projections, which are complicated maps, they are not surjective, and they're only, it just makes life very difficult. So let's just keep it in mind. But for instance, a good exercise to work out, also to get a little bit of sense of arc space and jet schemes, is to compute the jet scheme, the M jet scheme, for the following case. When X is, for instance, a node, let me just take 2 lines in the plane, or when X is equal to a cusp. And you will see in these simple examples, so really I want to think about this one as being a local picture of a node, and the other one being just a cusp. You already see in this very simple example, you can actually compute these things very explicitly. It's not too hard. That, for instance, the J schemes get very complicated. Already, you start going up on J schemes, you're going to get a lot of components. And most components don't map to other components. They are not surjected by components above. So you can try to figure out in this example, for instance, what is the limit of these arc spaces. So an important theorem here is the theorem of Kolchin. Which says the following thing. The arc space X infinity of a variety X is irreducible. In my definition of variety, I think about the variety as irreducible, of course. Otherwise, that would be false. But if I have a variety, then the arc space, even if X is singular, even if the J schemes acquire a lot of irreducible components, when you take the limit, most of the irreducible components don't really contribute to the limit, just because of lack of surjectivity of the maps. And what you get at the end is an irreducible space. So let me give a sketch of the proof. Of this theorem. So what you're going to do is that you're going to fix a resolution take from YF to X. You let E to be the exceptional locus of F. For instance, take a sequence of blow-ups, and then we resolve the singularities of X, and E will be the exceptional locus of the sequence of blow-ups. And then on the other side, take Z to be the image of E. So Z will be the indeterminacy locus of F inverse, where F is not defined. So the fact is that Y is smooth. So I know that Y infinity is irreducible. So in order to understand the X infinity, what I'm going to do is I'm going to put this resolution in the picture as follows. So you have X, which comes with its own arc space, X infinity, and I have Y, and this resolution F, and Y also has its own arc space, Y infinity. So if I have an arc on Y, it's given by a map from the germ of a disk to Y, I can compose with F, and I get an arc on X. So this defines the canonical way a map from Y infinity to X infinity. And this map is continuous. It's a continuous mapping on the arc spaces. So you notice that here I have this exceptional locus E, and here I have an indeterminate locus Z. So I can look at E infinity over E. I don't need this map, but of course they will sit inside Y infinity. And then Z infinity, the arcs lie entirely inside Z, will sit inside X infinity. So now I want to compare. I want to say something about this map F infinity. In fact, it's enough to show that F infinity is a dominant map, because we know that Y infinity is irreducible. If it's dominant, then the closure will be irreducible. So the claim is that this F infinity is dominant. So how do you see that? Let me maybe draw a picture. Suppose that this is Y, and this one is X. And somewhere here, I have Z, and over Z, I have this exceptional locus E. And everywhere else, the map is an isomorphism. So I want to show that every arc on X will lift to Y, or at least most of them. So the first thing I'm going to do is I suppose I have an arc alpha which sticks outside. Of course, if the arc is based outside the indeterminacy locus, then the map is locally étale. It's locally isomorphism, and I can lift whatever I want. So really, I need to worry about arcs which are least touching Z. So suppose that I start with an arc which starts from Z, so the base point is on Z, but eventually it's going to come out. So the final order of contact with Z. So I think about this. I've been a map from the disk D, delta, to, I call it alpha again. I map alpha from delta into X with this property. So when I look at the generic point is somewhere here where there's the head of the arrow. That actually is outside Z. So there is, again, I'm within the locus where F is an isomorphism, so I can lift that one. So I can certainly lift this part of the arc. So how do you think about that? You think about that as saying, you look at you remove the origin from the disk, from the formal disk, and you lift. So this sits inside there. So now the question is, the point is that this map here is proper. So by valuative criterion of properness, this is equivalent to say that given a diagram like this, I can find a unique lift. So there exists uniquely a lift after tilde. So what does it mean? It means that this generic point of the arc, this is sort of an open curve, can actually be closed up somewhere along the exceptional device or the exceptional locus, so that the image down is exactly equal to alpha. So this takes care of most of the point. It takes care of every point in here which doesn't belong to the infinity. So the only thing left to do now is to show that I can take care about the points on Z, the arcs entirely on Z. So I'm going to focus my attention on Z. So I have a nice vibration from E to Z. So, well, maybe the vibration is not very nice. For simplicity, let's say Z is just an irreducible set. So Z itself is a variety now. And E is also a variety, or maybe it has several components. Just I pick one of them, they become a variety. So maybe I restrict E to a set where it actually is smooth, and then I apply generic smoothness. So what happens is that generically, I can find an open set here and an open set here where the map is smooth. So given any arc in here, I can lift it up this way. Given alpha here, I can lift it up to an alpha here. So here is using generic smoothness. So this is going to take care of arcs in Z over an open set of Z. Of course, when I generate maybe some special point on Z, maybe the fiber is a multiple fiber, and there's no way I can lift, for instance, a smooth arc along a multiple fiber. But I don't care, because I can apply an induction. So induction will tell me that Z infinity is also irreducible, and therefore I can, the image of acts from here will fill up an open a dense set inside the infinity. And therefore the map is dominant. Once the map is dominant, then as I said, because this is irreducible, and therefore X infinity will be irreducible. Yes?
Are you saying, in fact, that F infinity implies the subject?
No, I didn't say that. Because there might be, maybe there is a multiple fiber here. So if I take an arc going down this way, which is maybe a smooth arc, I will never able to lift this one over there. But what can I do is I see this one as a limit of arcs on this open set. And those will lift. Yeah. In fact, that was exactly what I was going to write next. Is that a good example to work out is for instance, F infinity is not surjective in the following example. Suppose I take X to be the Witten umbrella, so this is X, Y square equal to Z square inside A3. Let's call it Witten umbrella. And why will be the normalization? Let me draw the picture of X. So this is a picture of the Witten umbrella. So I think about a family of smooth conics degenerating to a double line, for instance, in one direction, or there are three ways of looking at that, of course. And just make sure I get that right. So this is X, Y, and Z in my picture. So if you look at the smooth arc sticking out this way, then you realize that this one doesn't live to the normalization.
What does this theorem say? In general, that if X is any variety, then X infinity is irreducible. Or only, so here you said that in some case, for the cusp, for example, something fails, but the theorem says that it's irreducible or what?
So, okay, so you're asking about what is the theorem says exactly. The theorem says what it states, that for every variety, which is the variety is assumed to be irreducible, the arc space is irreducible. Now, if you look at the cusp, the J skins will have a lot of components. If you look at the example of a cusp, and you compute the J schemes, XM, so those will have a lot of components. But when you take the inverse limit, all these components will not matter. They're lost. And there's only one component at the inverse limit. So this is already give a good description. So now we have a good understanding of arc space of smooth variety, and generally the global structure of arc space of a singular variety. If you want to understand a little bit more about the structure of arc spaces, now we can focus on the fibers of the arc space of a singular locus. Or maybe we're going to focus on arcs through the singular locus. So this is exactly the inverse image and the projection map of the singular locus of X. So these are the arcs alpha over X, such that alpha 0 is in a point in a singular locus. So remember that this one, again, is smaller, but it still has infinite dimensional object. It still has not Noetherian and so on. So in general, there is nothing to say that this has a nice decomposition into a finite irreducible component. But this is actually the theorem of Nash. This is a finite decomposition. Into irreducible component. So this locus of x, so the singularity of x, will be just a finite union, and we call the index set I of reducible sets. So how do you prove something like this? The idea is, again, we gain information, we acquire information on arc space by looking at the same diagram as before. We look at the resolution, and we look at the diagram coming from the resolution. So you look at a resolution singularity. Here you have the arc space of x, and here you have the arc space of y. And so the first thing, let me call this map F. The first thing I'm going to do is that I'm going to take the inverse image of the singular locus on the resolution. So when I stay below, this is a Noetherian space. So this will actually have a, it's a variety of finite types. So this actually will have a finite decomposition. So there is some index set J, and some components I'm going to call EI. And so the J here is also a finite set. So that will be my irreducible decomposition of the inverse image of a singular locus in the resolutions. Think about, for instance, if you do blow-ups, central singular locus, there will be just the exceptional divisors of the map. So now I want to use this to realize the decomposition of the question is that I'm actually interested in the inverse image of the singular locus on the space of X. So if I look at any one of these components, think about this is an irreducible enclosed set inside here. So what I'm going to do is I can look at the inverse image on Y of this EI. So this is also irreducible enclosed because Y is the inverse image of a closed set, and Y is smooth. So this is still irreducible. And then when I take the image of this set on the other side. So these are all the arcs on X which are generated from arcs, which comes from arcs, the lift to arcs on Y that has order of contact 1. Yes?
Phi y minus 1? Or phi?
Minus 1, yes. Yes, I'm here too. So this is certainly irreducible. But here is actually a fundamental observation in the whole problem of understanding the structure of arc spaces. The fact that this map is continuous, it's almost a bijection. So most of it, in fact, we can actually consider as a bijection because of the uniqueness of lifting of arcs away from arcs entirely contained into the indeterminacy locus. But it's not a homomorphism, or in any case, it's not a closed map. So in general, this may fail to be closed, even if this is closed. So in order to take a nice, looking at the composition into reducible sets, I'm going to take the closure. So let me give a name to this. I'm going to call this NEI. And now, by taking this closure, maybe implicit in using some of the arguments I explained before, you can check that this reducible decomposition will give rise to some irreducible decomposition of the set of arcs of the singularity. And so the only thing is that I might not need to use all exception all elements in J. So I may actually refine this union when I go on the other side. So in fact, this will be is a Moller set. So I is some smaller set inside J, potentially smaller set. So the point is that you see an element J belongs to J minus I if and only if the corresponding set in arc spaces is actually contained in some EI for some I in I. No, I didn't. I think it's correct. So the one index here are the maximal one under inclusion. It's all right? Yeah. So what happened is that over here, all these components, they may overlap a little bit, but generically, they're not. There is no adherence between each other. But when I map to the arc space, some of this set of arcs coming from one side will actually lie in the closure of the other set. And this is really the point. The point we would like to understand. We were able to recognize which one are those that survive in index set I. So here I take I minimal with this property. By taking I minimal, then I ensure that this is really the way I would write the composition of a set into reducible components. So one way actually of thinking about this problem is the fact that F infinity, you can consider it for most of it, almost everywhere, to be a bijection, a continuous map, bijective map. But it's changing, the topology is changing, and we're trying to measure how much the topology is changing. And there are several ways to measure. Now this is the first approach to understand, one point of view on understanding the measure of changing the topology. In the second part of my lectures, I will talk about a way of actually quantifying by looking at some condimensions, for instance. So, you see, for each one of this set in the decomposition here, so I take I here is in the set I. Hold on, the lost. So if I look at alpha I, this is I look at a generic point. So again, this is an irreducible set in a scheme, so it has a generic point. Let's call it alpha I, and associate to this the valuation alpha I. So this is a, if you think about the generic point here, it lifts, is the image of the generic point on this set here, which is an arc, generically a contact one with the exception divisor. So it's not very hard to see that the valuation I pick up in this way by pulling back a function back to y is the same as the valuation defined by EI, which is simply you take any rational function, you pull it back to y, and just look at the order of 0 pole along the divisor. So evaluation of the, yeah. So this is a distinct divisor evaluation. By distinct, I mean that if I change my index, then I'm going to pick up a different divisor, so a different divisor evaluation. So I'm going to give this definition. I'm going to say we call any such valuation a Nash valuation over X. And the important thing to remember is that they only depend on the structure of the arc space. So this is really the set of Nash valuation, which is a finite set in the set of divisor evaluation, is an intrinsic set. So it doesn't depend on choices. This divisor will depend on the choice of resolution, for instance. I can ask the following question. which valuations arise in this way. So I wanted to work out an, let's see. Well, let me maybe finish. So let me rephrase the definition as follows. Given a divisor evaluation, you look at evaluation of E, where E now is maybe inside Y is a prime divisor, and Y is a resolution of X. So we say that the evaluation, this evaluation of E is a Nash valuation over X if the corresponding set defined as before is an irreducible component or the inverse image or the set of arcs, so a singularity of X. So this is just rephrasing the definition of Nash valuation. I can think about this as being some sort of the center of evaluation of E inside X infinity. I will be more precise about this. This is not really a definition. I will be more precise in my last lecture about general definition of. I will use a different word. But think about it as a center, so it's a closure of the generic point or in some sense. So the Nash idea, when Nash actually asked this question, is, well, I sort of see two ways of looking at singularities. One is by looking at the arcs of singularities, another is looking at, for instance, divisors over in a resolution of singularity. And is there maybe a way to relate the two? So of course, resolution singularities are not unique. And so one needs to be a little bit careful, because if I blow up further, I will not generate more components here, but I generate more divisors here. So I need to find a way of detecting a smaller set of divisors somehow. So what they call essential divisors. So the definition here is that the evaluation E is essential over X. If well, before I give the definition, let's think about the case of a surface. So suppose that X is a surface, like say a normal surface. Then I look at the minimum resolution, and well, that's the most natural place to look at. Every resolution will dominate the minimum resolution. Minimum resolution comes with a bunch of divisors, and we can ask, are those the divisors, do they actually all correspond to distinct components in the arc space? And but in higher dimension, it's more problematic. First of all, because there is not a minimum resolution. Second, because you have like resolution which are not divisorial, meaning that the locus is not pure dimension 1. Like, for instance, a small resolution. The exceptional locus is doesn't extract any divisor, so one needs to be careful about that. So he came up with the following idea. Let's look at all resolutions and test this a divisor evaluation be essential if the center is an irreducible component over the singular locus. So he said evaluation is essential over X if for any resolution, let me use a different letter now, G from X prime to X, the center inside X prime of the evaluation is equal to an irreducible component of the inverse image of the singular locus. Okay. So we have these two definitions, And the idea of Nash is that we should look at these two definitions and try to compare them in a way of comparing the arc space of a variety with the resolutions of the variety. So it's not hard to see that if you look at the resolution and you take another blow up, that divisor, I mean, maybe you blow up a center which is strictly contained into the component, some component of the inverse image of single locus, that will not give you a Nash component in the arc space. So another way of phrasing this is that the remark here is that every Nash valuation over X is essential over X. So how do we think about that? So let's look at the set of all irreducible components of the inverse image of the arcs of the singularity. So this is a set we've been interested in trying to understand. So we identified this set with a set of valuations that we call the Nash valuations. So here there is another set of valuations that come from the resolution singularities, which are the one called essential. And by this remark, that I didn't really explain, but it's not hard to convince yourself it's true. I have an inclusion here within the space of divisor evaluation. So there is a bigger set of divisor evaluation. Essential evaluations are a subset of those, a finite subset. This is also a finite subset is included in there. So in this way, I actually constructed a map denoted by n of x, sub x. This is called the Nash map. And you notice that this is injective. So eventually, I'm gonna forget about the map starting from this geometric object, but rather thinking just in terms of valuation. I think it's just more natural, at least to me. But that's the Nash map. So the question that Nash asked, it became famous as the Nash problem. Is the following. Is a Nash map always surjective? So that was his hope. And notice that this actually came with very little evidence. So in dimension 2, let's think for a moment again. We have a minimal resolution. If you blow up further, every new divisor will actually map down to a point. This is not an irreducible component. So we see the essential evaluation with respect to E is essential if and only if E is an exception divisor in the minimal resolution. Okay, the minimal resolution extracts a bunch of divisors, always the resolution we're looking at. Those are the essential divisors. And this actually is a setting in which Nash was more convinced the question to be correct. But as far as I remember, he computed the case of AN singularities. I was actually hoping to get the time to write down the computation for A2 singularity, which is very explicit, very nice, to see the correspondence. But even the next simplest examples actually become more and more complicated. The idea is that if you actually try to handle this by looking at the equations of the singularities, the complexity grows very, very fast. And so there has been this. Maybe I should mention this problem goes back to the late 60s, and there's been a lot of work through the years. But especially on the surface case. But let me just mention that after many partial results, there was this. Let me just say the last theorem, which actually solved this problem in affirmative in a surface case, which is due to Fernandez de Bobadilla and Peperera, is that in dimension 2, the Nash map is always surjective. So the point is that at a certain point you realize that you cannot just work with the equation, you need to find some new way of tackling the problem. And so there's definitely a lot of new ideas in this proof. Essentially, what they actually use is some topological argument, in fact, to study arcs on a surface singularity, and they put it this is the case. This is a very recent theorem, just a couple of years ago. So I will actually give a proof. I will not give the original proof, but we'll explain a proof of this theorem tomorrow. So in dimension 3, there are several cases which are known to hold. So various people worked, and then maybe we mention more next time. Let me just maybe mention, for example, the conjecture is this question is known to be true in affirmative in the toric case. And I will talk more about this, maybe just mention the name later. Or I just mention it here now. So this is done by Ishii and Kollar. But in general, but in any dimension greater than 3, there are counterexamples. So, meaning where the Nash map is not surjective. So tomorrow I will explain one example, maybe state a general class of examples as well, and then try to prove a theorem that will actually settle the two-dimensional case. But in fact, I will actually say the theorem in more generality. There are still some. One can rephrase the problem. So in the moment you realize that the problem actually is a negative answer, then you just try to find a better formulation, hoping that will lead to some understanding of still of this structure, the arc space. Even if the first guess was not correct. And maybe just before I conclude, I think I feel like I should mention that if you read in Nash's paper, while he's pretty confident of the two-dimensional case, which turned out to be correct, in fact, he doesn't state this as a problem or conjecture in high dimension. It's just that as a question. But I think you can feel from the line where the question is phrased that he was not really sure that what answer to expect, I think. Anyway, so maybe stop here for today. Yeah.
So for the case of dimension 3, it's still an open problem if the Nash function is surjective?
No, in any dimension greater or equal than 3, it's false. Oh, yeah, greater or equal than 3. So I didn't write that. Yeah. So the first examples were in dimension 4 and higher, but then there are other examples that works in dimension 3.
Could you quickly remind me what the center of evaluation is?
Oh, yeah. So in a very concrete terms, for a divisor evaluation, so he's asking about the center. So if you have a divisor E on some Y and down to X, then what you can look is just look inside here the image of E. So this is an irreducible set. Where is who was asking? Oh, there it is. This is an irreducible set, and that's called the center. That's one definition of center. But there is another definition of center, which would give the generic point, which given and this is actually more general given evaluation. You look at the evaluation ring inside the function field, and then you restrict the maximal ideal to the ring of functional X, and that will become some prime ideal, and that will be the center too. Yeah.
So this is connected to the Kolchin theorem. What happens if so X is irreducible, and instead of X infinity you look only at curves passing through a fixed point? Would you think that then also this set of curves is irreducible?
No, because this is exactly, if you like, this is a particular case of this Nash problem. So suppose, for instance, that X has an isolated singularity, and suppose that the A2 singularity. Unfortunately, I didn't work out the examples. But A2 singularity, when you blow up, you get to these two exception divisors, and it's easy to see from the equation. You get two families of arcs with a singular point. So that is the inverse image of a singular point. But again, it may have more components.